Welcome to A-Level and AP Physics. In today's lesson, we will discuss past paper questions from March 2024, Paper 4, Variant 2. As always we will discuss these questions in detail so you can improve your conceptual understanding of physics and also you can have better understanding of these exam questions. Let's study together, let's improve together. Question 9, part A says, electrons in a vacuum are accelerated through a potential difference of 84 kilovolts. The electrons then strike a metal target and X-rays are produced. Calculate the minimum wavelength of the X-rays that are produced. Minimum wavelength means that the total kinetic energy has been converted into energy of X-ray photon, and total kinetic energy is equal to the electrical energy. So simply you can start from here. We can say Q times delta V. The gain in kinetic energy is equal to the electrical energy supplied, and this is electrical energy supplied, and this is equal to energy of X-ray photon. So this is energy of single photon and this is energy gained by single electron. So we need to find out value of lambda. So we can say lambda minimum in this case will be equal to Hc over Q times delta V. Value of H is a Planck's constant, that is equal to 6.63 times 10 to minus 34, and C is a constant, that is equal to 3.0 times 10 to 8. These two constants are very important for quantum physics. Then Q is the charge on single electron, 1.6 times 10 to minus 19 coulombs, and delta V is the potential difference, that is equal to 84 kilovolts. Now if we simplify, in this case we will get 1.5 times 10 to minus 11 meters. So this is the minimum wavelength. So if you have done this one, you will get 2 marks for this question. Second part says the melting points of two metals are given in table 9.1. Copper melting point is given and tungsten melting point is given. Suggest why the metal target is made from tungsten rather than copper. Because melting point of tungsten is much higher than melting point of copper, and during X-ray a lot of energy is converted into thermal energy. About 99% energy is converted into thermal energy, means the kinetic energy of electrons is converted into thermal energy, and this is roughly 99%. So only 1% kinetic energy of electron is converted into X-ray photon. So we need metal with a higher melting point. That's the reason we use tungsten. Now let me show you the answer, how you can write down the answer. So this is how you can write down the answer. This question has 2 marks. So first mark, you can say some kinetic energy of electrons is converted into thermal energy at target absorbed by tungsten. Tungsten does not melt quickly because it has a higher melting point. So if you write on these 2 points, you will get 2 marks. Part B says an X-ray beam is incident normally on a sample of soft tissue and bone as shown in figure 9.1. Data for the two materials are given in table 9.2. So we have value of attenuation coefficient and also we have values of specific acoustic impedance. The total thickness of soft tissue is X. Total thickness of bone is also X. The incident intensity of the X-ray beam is I naught. The transmitted intensity of X-ray beam is 13% of the incident intensity. Determine X in centimeters. So how we can answer this question? The simpler way to answer this question is, first of all, simply we can combine soft tissue. So here, so we can combine here. So this is representing soft tissues, and here we have the bone. So this second part is the bone. So this is soft tissue, so we can write on here. So here we have soft tissue and this one is representing bone. Thickness of this one is X, so this thickness is given. This thickness is X and this thickness is also X. So here we have intensity, this is I naught. At this point, let's say intensity become I1 and here intensity is I2. In the question it is given to us that I2 is equal to 13% of I naught. So here we have I naught. So it simply means that I2 is equal to 0.13 1 theory, or you can say 13 divided by 100 I naught. So we can say I2 divided by I naught. This is equal to 0.1 theory. Now first of all, if you look at soft tissue, for this one we can write down I1 over I naught. This one will be equal to e to the power of negative mu x. So here we have mu x. So we can say this is mu 1. So at this point we can say I1, this one will be equal to I naught e to the power of negative mu x. Even you can just start with this one. So we have I1 here. And at this point I2 we can write down. I2 will be equal to intensity at this point. In this case we are talking about X-rays, so we ignore reflection. So here we have I1, this is equal to e to the power of mu 2 times x. Now this I1 we can replace with this value I1. So I1 we can write down, this is I naught e to the power of negative mu 1 x. And here we have e to the power of negative mu 2 x. I2 by I naught we have here. So we have here. And we can write down this here. We have a little bit more space. So we can say I naught by I2. Actually, this is I2. We have I2 divided by I naught. This is equal to 0.1 theory. So you can even clear this part. So if you want to clear, you can clear this one. So let me clear this. So this is I2 by I naught, and this is equal to e to the power of negative mu 1. We have 0.22, this is 0.22 x, and here we have e to the power of negative 3.0 times x. So we need to find out value of x from here. Value of x. So this is e to the power. So simply we can say this is 0.1 theory. Here we have e to the power. We can combine these two. We will get 3.22 x. Now if we take ln on both sides, so we can take ln of 0.1 theory. So here we will have ln of e. So we will have minus 3.22 x. So x from here will be equal to ln 0.1 theory divided by, we have negative 3.22, and we will get our final answer. That will be equal to 0.63 centimeters, because the unit of mu is centimeter. So this is our final answer. This is how you can calculate. C1 says define the specific acoustic impedance of a medium. Acoustic impedance, simply Z is equal to rho times C. Rho is the density of the medium, so you need to understand this is density of the medium, and C is the speed of ultrasound in that medium. So this is speed of ultrasound in that medium, and the product of these two quantities is called specific acoustic impedance. Now let me show you the answer, how you can write down the answer. For the answer of this question, simply you can say product of density and speed of ultrasound in medium. Second part says use data from table 9.2 to calculate the percentage of the intensity of ultrasound that is transmitted at a boundary between a soft tissue and bone. So for this purpose, simply we can draw first of all. So you can take any boundary between soft tissue. So this is soft tissue, and here we have the bone. So this one is the bone. So we can take any boundary. Let's say we take this boundary, and we assume at this point intensity is I naught. So this is the intensity I naught. In from here IR will be reflected, so we can say this is IR, and IT will be transmitted. So this will be IT. So IT will be transmitted. We need to calculate fraction transmitted. So we can say fraction transmitted. This is what we need to calculate. Fraction transmitted. Fraction transmitted will be equal to 1.0 minus fraction reflected. Fraction reflected. This is based on conservation of energy. So this is fraction reflected. So if we can calculate fraction refracted, so we can find out fraction transmitted. And if we have fraction transmitted, then we can find out percentage transmitted. So simply we can find out percentage transmitted, that will be equal to fraction transmitted. So this is how you need to answer the question. Fraction transmitted time 100. So this will be time 100. So we can find out percentage. So we need to work out fraction transmitted, fraction reflected. So we need fraction reflected, and fraction reflected means this is equal to IR over I naught. This one will be equal to Z1 minus Z2, Z1 minus Z2 square over Z1 plus Z2 square. So this is acoustic impedance of medium. So we have Z1 in this case. So Z1 we are taking this value bigger, and this is Z2. It doesn't matter which one you take, Z1, which one you take Z2, result will be the same because we have square here. So we have Z1 that is equal to 7.8 minus we have 1.7 square of this divided by we have 7.8 plus we have 1.7 square of this. Now if we solve this one, we will get 0.41. So means 41% is reflected, so 59% will be transmitted. So we can get this is, so we will get here, so this is 1.0 minus we have 0.41, so we will get 0.59. So if we multiply 0.59 with 100, so we will get 59%. So this is 59%. So simply we can say this is 59. So this is how you need to answer this question. So one thing more you need to understand is that 1 is equal to IR over I naught for your better understanding, plus this is IT over I naught. So if you take LCM from here, for example, you will take this is I naught, so this is IR plus IT. So it means IR plus IT, this is also equal to I naught. So here, so intensity here you can say incident is equal to IR plus IT. Third part says the ultrasound is now incident on a sample of soft tissue and bone shown in figure 9.1. Suggests two reasons why the transmitted intensity through the sample is less than the answer in C2. In C2 we have found fraction transmitted. In the last part, in the second part, we have found that fraction transmitted is equal to 0.59. Fraction transmitted is equal to 0.59, and in that case we have just considered one boundary. So we said this is the soft tissue and here is the bone. We just considered one boundary, so this is the point you need to understand. So in this case we just considered this one boundary, So let me change color so you can understand this one better. So we consider just one boundary, mean this one boundary we considered. But if you look at this one, here we have more than one boundary. So you can say we have one boundary here, we have one boundary here. So it means here we have more reflections. So we can say more reflections. If more reflections, it means that transmitted intensity, this intensity will go down. So this is one reason. The second reason is when ultrasound waves, they pass through the medium, some of ultrasound waves, they will be absorbed, so ultrasound will be attenuated. So you can say the second reason. One reason, more reflections. Second, you can say absorption. So this can be the second reason, absorption in soft tissue and bone. So these two reasons you can write on. This answer need two reasons. Now let me show you the answer, how you can write down the answer. In the answer, you can mention these 2 points, more than one boundary, so more reflections, so transmitted intensity will be lower, and some ultrasound is absorbed in the soft tissue and bone. You can also say in the matter. Matter means soft tissue and bone. Question 10 part A says the sun has a surface temperature of 5780 kelvins. The luminosity of the sun is 3.85 times 10 to 26 watts. Calculate the radius of the sun. So simply we have to use Stephen-Boltzmann law. According to Stephen-Boltzmann law, luminosity is equal to sigma A. A is the surface area times T to the power of 4. This is absolute temperature. So we need to find the radius. We can write down the surface area. This is 4 pi r square times T to the power of 4. We need to find out r, so we can say this will be equal to L divided by sigma 4 pi times T to the power of 4. And we need to take square root of this. Now simply plug in values and you will be able to find the answer. Luminosity is 3.85 times 10 to 26, and this is divided by sigma. Sigma is 5.67 times 10 to minus 8, and here we have 4 pi, and temperature we have already in Kelvin. This has to be in Kelvin. So we have 5780. If we take root of this one, we will get value of r. R will be equal to 6.96 times 10 to 8 meters. So this one is the radius of the sun. So we can write on here 6.96 times 10 to 8 meters. Just little typo here. So the power of this one is 4, because here we have 4, so power here also has to be 4. Second part says the earth is a distance of 1.50 times 10 to 11 meters from the sun. Calculate the radiant flux intensity F of the radiation from the sun at a distance of 1.50 times 10 to 11 meters. Give a unit with your answer. So simply we need to calculate radiant flux intensity, that is F, and F is equal to power over surface area. So this is equal to power over surface area of that sphere. So we can simply write on A. So power in this case is the luminosity, and here we have this is 4 pi t square. Let me explain you a little bit this one in detail. So in this case what we are saying is that D is the distance from center to here. So this sun is located here and our planet is located here, so at this point. So this D is the distance, and luminosity of the sun is here, means the energy emitted per second by the sun, that we have in the last part, and that was equal to 3.85 times 10 to 26 watts. Now simply we need to plug in values and we can find value of F. So this is 3.85 times 10 to 26 divided by, we have 4 pi times, we have 1.50. D is 1.50. So we can plug in here 1.50 times 10 to 11 square of this quantity. And if we simplify this one, we will get 1.36 times 10 to 3 watts, and unit of distance is meter square, so per meter square. So we can write on here 1.36 times 10 to 3 watts per square meter. So the power of luminosity is watt, power of distance is meter. So this is simply how you need to answer. Third part says the variation with wavelength of the intensity of radiation emitted from the sun is shown in figure 10.1. Another star has the same radius as the sun but has a lower surface temperature. On figure 10.1, sketch a line to show the variation with wavelength of the intensity of radiation emitted for this star. So first of all, we can look at the luminosity of the star. Luminosity is equal to sigma 4 pi r square times t to the power of 4. Radius is the same, surface temperature is lower, it means luminosity is lower. Now we can determine the wavelength, peak wavelength. by Wien's displacement law. So we can say Wien's law I'm writing. So you can say Wien's displacement law, lambda peak times surface temperature. So this is surface temperature. You have to be clear about this one. This is equal to constant. So the product is equal to constant. If surface temperature go down, it means this lambda, as luminosity is lower, so it means intensity is also lower, means lambda is longer, so intensity is also lower. Now we need to sketch the curve. Before we sketch the curve, let me show you this figure. Understanding of this figure is important. So you can see the trend here. When lambda is longer, how about intensity? So you can see as lambda is getting longer, peak intensity is decreasing. So you can see here peak intensity is decreasing. So this is the main concept you need to understand, that lambda peak times T surface temperature, this is equal to constant, and this is based on Wien's displacement law. And based on this one we need to sketch the curve now. So we can draw the line here. So this is peak, so the next peak has to be lower and it has to be at longer wavelength. So it has to be somewhat like this, higher, means longer wavelength. And now simply we can connect this, it has to be always lower. So this is how you can sketch the curve. And if you have drawn this one, you will get 2 marks. Wavelength has to be longer and the peak intensity has to be lower. Part B says a galaxy in the constellation Corona Borealis is moving away from the Earth. The visible emission spectrum for the Sun is shown in figure 10.2. The lines are at wavelengths of 397, 410, 434, 486 and 656 nanometers. The compositions of the Sun and a star in the Corona Borealis galaxy are similar. On figure 10.3, sketch the emission spectrum for the star in the Corona Borealis galaxy as observed from the Earth. No calculations are required. Sketch the emission spectrum. Means these lines simply you need to sketch. So in this case here we have 350 and this is 400. So it means it is divided into 5 equal parts and one part is representing 10. So this is 397. So it means this has to be very close to 400. Very close to 400. So I can simply draw the line here. So you need to draw the line here. So this is. Next one is 410. So 1/5 of this total, this distance, you have to divide into 5 equal parts and one part is 10. So we can draw about here. So this is just about is quite enough. Next one is 434. So 400, 450, 425 is halfway. So I'm assuming this is about a halfway here. So I can draw a little bit next to this one. So it has to be little after half. Little after half. So we can draw, this is about 1/5. So it will be little bit here. So this is 486. 486 means here. So this has to be here. So you have to be a little bit careful with this, but just approximate is okay. You can use meter rule and you can find 1/5 around here. 656. So this is 650. So again 656, it will be around here at this point. So this is how you need to draw these lines. You can use meter rule actually and you can draw them in a proper way. I've just drawn approximate locations. Second part says the galaxy in Corona Borealis is moving away from the Earth at a speed of 21,400 kilometers per second. Use information from B1 to calculate in nanometers the observed wavelength of the lowest visible energy emission for the star in the Corona Borealis galaxy. Lowest visible energy. Lowest visible energy, so E minimum, it means that we have to consider the maximum value from the visible energy spectrum, lambda max. And also galaxy is moving away, so even lambda will increase. So we can say the value of lambda will be equal to the lambda max plus change in wavelength due to redshift. So we can say delta lambda. Lambda max from part B1 we have that was equal to 656 nanometers plus delta lambda. So this value we need. Delta lambda simply we can calculate. This is delta lambda over lambda is equal to V over C. Delta lambda will be equal to V times lambda divided by C. V is 21,400 kilometers per second, so you have to multiply by 1000. So this is meters per second divided by C, that is 3 times 10 to 8 meters per second multiplied by lambda, that is 656 nanometers. So you no need to convert unit here because this meter per second will be cancelled, so unit is nanometer. Now if we solve this one, we will get 46.8 nanometers. 46.8 nanometers. So simply we can write it here 46.8 nanometers. So if we solve this one, our answer is up to 3SF 703. So this is how we can answer the question. So you need to understand what question is asking you and then look at the given informations and try to use your understanding of physics to reach the final answer. Third part says the wavelength in B2 is used to calculate a value for the surface temperature of the star in the Corona Borealis galaxy. The calculation does not give an accurate value. State and explain whether this value of temperature is too high or too low. First of all, we need to understand the value of lambda we have calculated in the last part. That value is the maximum value. And that maximum value actually is not the peak value. So we can say it's not equal to the lambda peak of intensity against lambda curve. As lambda max, what we have calculated in the last part, that is greater than lambda peak, actual value of lambda peak, by Wien's displacement law. So we can say lambda peak times surface temperature. So here we will say surface temperature. This one has to be equal to constant. So if we assume lambda p is equal to lambda max, for example, this value will be very high. We're using the maximum possible value of lambda. So it means this temperature, surface temperature of the star, based on this calculation, has to be very low. So this one point simply you need to write down. So how we can write down the answer? For the answer, we can simply say peak wavelength too high means we are saying this is peak wavelength. We are using this value for the peak wavelength. So temperature will be too low. So if you say temperature will be low because peak wavelength is too high, you will get 1 mark. That's all for today's lesson and also for this paper. I hope these videos are helpful and these videos are helping you to improve your understanding of physics. If this is the case, so please like and subscribe because your encouragement is very important. And if you're looking for extra resources, you can also join Patreon. On Patreon, you will see more resources, not only video, a lot more than videos. See you next video.